You guys ready? Let's do it. Welcome back, everybody. We'll have a discussion today about credibility and confidence. We've already seen an example, and we played around with this a little bit on our homework. So in the normal example, a Bayesian's going to build their distribution on mu. Let's say they use a flat prior. It'd be a normal distribution centered at x bar with variance sigma squared over n. And they would build their interval out of that. They would center their interval at x bar, and then they would probably look two standard errors out, 1.96 standard errors. This is a conversation we've already had. The non-Bayesian has different ways to think about that exact same interval. Do you guys know what a pivot is? So a pivotal quantity? So basically what they do is they rearrange a probability statement. So they write down some statement about x bar. So frequentist test statistic for estimating mu might be x bar. It's unbiased. It's minimal variance. And then we can look at the variability of that test statistic, which is a different way of thinking about things. The variability of the test statistic is sigma squared over n. And so they would write down a probability statement about x bar. It'd be normally distributed. It would be centered around mu. And they would have variance sigma squared over n. And so, i.e. the expectation of x bar is mu. So we're talking about the normal case with known variance. And then they pivot. They rearrange their statement. So let me just write it down. So what we had seen before, so this is kind of the classical way of saying things. I won't go into the technical details about what is a pivotal quantity, but it's a quantity that does not concern the parameter directly. So we're not going to get into technicalities, but what you might do is think about something like this. So this might be centered around mu plus 1.96. And then you might have this centered around mu minus 1.96. I think we said this before, that a classicist, or maybe a frequentist or something like that. So the classical version of statistics is to think about a test statistic that estimates your parameter and then describe its variability. A Bayesian does something different. They put a probability distribution on the parameter itself, and then they can measure the variability through that probability distribution. So they're looking at the same object the whole time. Sometimes you get the same answers, but the interpretations are different. So pivoting means that I'm just going to rearrange all this stuff. So I can rearrange the x bar with the mu's, where everything is shifted. So just by a little bit of plus and minusing, averaging, I should just say rearranging the terms on each side, we can come up with two different inequalities. And you could write down this statement. X bar plus 1.96 and x bar minus 1.96. Oh, and this has sigma over root n. I forgot that part. Same thing over here. Sigma over root n, sigma over root n. So the 1.96 times the standard error, two standard errors in a normal distribution, encapsulates about 95% of the probability. It's close enough that nobody ever quibbles over the little rounding error that's being made. So the probability statement for a classicist is on the test statistic itself. And so when they rewrite this, this is called pivoting. They didn't make a probability statement on the parameter itself. That's what a Bayesian does through Bayes' rule. But they're talking about the probability of these left and right limits. And how do they interpret it? They interpret it through maybe coverage or something like that. So there's a frequentist aspect to this, that set will cover the truth 95% of the time. If you were a Bayesian and you used a flat prior on the same thing, you would come up with an explicit probability distribution about mu. And these things would be fixed. So this would be a belief statement about the true mean, where it lives. Personally, I really like that duality. in there that they're the same answers. And I can interpret it two different ways, and that's pretty good. So I can't ask for more. So I call that alignment, agreement. Two different ways of thinking about it. Both are equally valid. Of course, you would have to tell people I used a shift prior or something like that, and I had all kinds of good reasons for picking that. This isn't a very compelling thing because the Bayesian and the non-Bayesian do come up with the same answers, and they're both good answers with totally different interpretations. Sometimes this doesn't happen. And I want to point out, this is happening here because of the symmetric nature of x bar and mu. So if you wrote out the likelihood function, and we're using a flat prior, so that's not going to change that symmetry in the relationship between mu and x bar, and the Bayesian and the non-Bayesian are flipping those two things. But if there's symmetry, flipping something that's symmetric doesn't really change anything. That doesn't always happen. So there's good reasons why it happens in this case. We've already seen for the beta binomial thing, even though the asymptotic coverage interval does converge in some sense, it converges in a very funny manner. For any particular data set, I don't know that it's frequentist. It's frequentist in the limit, and it gets more and more like the frequentist thing that you're after is n bigger. So, but it can kind of jump away sometimes. So that kind of makes me a little bit worried as well. I think that we could probably agree that the Bayesian answer is better. So it covers better. We'll see other good reasons why we like that beta half-half prior. If you used a really bad prior, the Bayesian answer wouldn't be very good. So obviously there's a trade-off there, and you want to think about why you're coming up with priors. But a Bayesian can cover better than maybe an asymptotic frequentist. I will point out there is something called the exact interval that you could construct, and it's pretty jumpy as well. There's corrections to that interval, and usually they build in like a penalty, like they'll add a half and a half to the successes and the failures. The most common thing that I see people do is they add 2 successes and 2 failures. So it's like building extra bias. It's like using like something like a beta 2-2, which would, I don't know, depends on how much data you had. So my point is that the Bayesian and the non-Bayesian think about this problem totally differently, but we do come up with the same answers. What we think is random, or what we're placing the random measure on, I think we all agree the data was random. But given that I've seen that random data, I can use the likelihood to express my beliefs. So we use that random process to build our likelihood in the first place. So I do agree that the data was random. And mu, being a random variable, doesn't trouble me at all. It might be a fixed quantity, but I'm uncertain about what it is. And you can use a random variable to model something that's fixed in nature. So that doesn't bother me. Let me show you an example today where the Bayesian and the non-Bayesian might totally disagree with each other. So let's look at this example. I'll send you a paper, I'll put it up online, and you can read through it, and this example comes from this paper. So this is one of those traditional problems to spur debate between Bayesians and non-Bayesians. So I've been in those debates many times. It never gets won for some reason. I've never been able to compel a frequentist with this. But we can talk about that later. So here's our example. I'm going to say that I'm going to get one of 2 values. It's going to be either theta plus 1, so we'll observe theta plus 1, or I'll say with probability we'll make this fixed, or we'll observe theta minus 1 with probability 1/2. So I'm going to take a coin flip. So I'm going to have a random variable, and it takes on the values theta plus 1 or theta minus 1. I'll even tell you what the probabilities are. It's fair coin. This doesn't make a big difference in the problem. You'll see this once we work through our example. This is the parameter of interest. So we don't know theta. So our goal is to infer theta. And maybe we want to infer it in terms of possible values of theta, sort of thing. So we might want to give you a set. I'm going to interchange the word interval for set here. I hope you can understand that an interval is a set. It's an infinite collection. So it's uncountable. It's big. But I can come up with the same notion for discrete things and see if they cover the truth as well. And so our goal is to learn theta. So I'll write down sets, but this could pertain to intervals as well. So let me just write this down again. So xi is going to be either theta plus 1 or theta minus 1. This happens with probability p. This happens with probability 1 minus p. And we'll let p be 1/2. So that's 1/2. So this is a Bernoulli trial, but it's a little bit different. A lot of times we know what sort of things we're going to see from the Bernoulli. In this example, we're not sure before we start the process even what the values of that random variable is. We'll let theta be anything. So let's say theta lives between negative infinity and infinity. So a priori can take on any value whatsoever. Let me just ask you, what is the nature of theta in this problem? How would you interpret that parameter?
Mean.
Shift, yeah, but it's something like a mean too. So you could think of it as a mean, a location parameter, or a shift parameter. So I think all those are accurate in this case. So it's a shift parameter. Okay, let me show you, I'm just going to throw this out there, we'll discuss it for a minute, a classical solution to this problem in terms of coming up with a confidence set. So the confidence thing means that it's supposed to cover. That's what it means. That's part of the technical definition. And you can, if you say it's the asymptotic confidence interval, it means is n gets big, and if it's the exact thing, it's supposed to cover exactly. But sometimes they're not exactly perfect. They're kind of in the ballpark. You can make things perfect, but I never like those answers if the data shouldn't tell you something that's perfect, like in the binomial example. Okay, here's a 75% confidence set, or yeah, confidence set. So a 75% confidence set is this. And I'm going to say we get to observe two values from this. So we observe, I'll tell you what the data looks like. This is important in the problem. Two random IID draws from the process. So I'll either get theta plus 1 twice, or I'll get theta minus 1 twice, or I'll get a theta minus 1 and a theta plus 1. There's two different ways I could get those. So my confidence set, this is a function of the data. I'm just going to come up with some notation. So remember what a confidence set is, though. It's an a priori statement about covering. So it's a statement about the way you are doing statistics. So maybe 75% of the time with people that come into my office, I'll give them correct answers, i.e. I will cover the truth. And 25% of the time, I give people bad answers. What does it mean about their specific problem? Conditional on the data that they saw? I'm not talking about that. I'm talking about different people coming into my office with this problem. I have this queue of people, they're each holding two numbers, and they're like, give me a set for theta. And 75% of them, I do justice by them. I give them correct answers. I cover the truth, and 25% of them get bad answers, and none of them know who they are. That's the problem. So we'll rationalize that this is a 75% coverage set in a second. So there's going to be one of two cases. So either I'm going to have x1 is different from x2, so they're different answers, or I have x1 is equal to x2. So I have the same answers. So in this case, things are either I saw theta plus 1 twice, or theta minus 1 twice. And in this setup, I've seen theta plus 1 and theta minus 1. You should realize instantaneously these are very different situations. So I'm going to report back this answer if these things are different. I'm going to take x1 plus x2, and I'm going to divide it by 2. And very arbitrarily, I'm going to do something different right here. So I'm going to report back x1 minus 1. If the answer is the same. You might be thinking, why didn't I take x1 plus 1? And I could have done that too. And it also would have been a 75% coverage set. So if I had replaced this with that, that's also 75%. They're both 75%. Let's figure this out real quick. It's just a little bit of arithmetic. So let's imagine I have a theta plus 1 here, and a theta minus 1. Kind of assuming I knew which one that was. So it doesn't matter, you can flip the order of that and it's still exactly the same thing. We're just adding. So what's this right here? This is 2 theta. Divided by 2, it's theta. So this thing is equal to theta. Always. When that's true. So conditional on that true, I will be giving a correct answer. So this is correct if I've observed theta plus 1. So if this is theta plus 1, subtracting off 1 gives you theta. If this was theta minus 1, it does not cover the truth. So if this was theta minus 1 that we got right here, minus 1, I'll be reporting to the scientist that I think your answer is theta minus 2. So I will have given them an incorrect answer. But if I got lucky, and this was theta plus 1 right here for x1, then that would be equal to theta. So I said this is, given that this is true, right here, x1 and x2, this covers 100% of the time. So this has 100% coverage in that scenario. And in this scenario, this covers 50% of the time. It's either theta plus 1 or theta minus 1. Of course, if I change these probabilities, I would have just changed that frequency. So you're going to have to know one of them to solve this problem. But it would change the frequency. But the reason I came up with 75% is because this happens 50% of the time, and that happens 50% of the time. And that's because of this probability being 1/2. So let's just imagine I flipped the coin the first time. I've either got theta plus 1 or theta minus 1. So the second coin flip that's going to happen with probability 0.5 is either going to match the first entry or it's going to be different. So they either match with probability 0.5 or they differ with probability 0.5. So this happens 50% of the time. This happens 50% of the time. So the total coverage rate, if we're in this case right here, I cover 100% of the time. X1 is not equal to X2, and that happens half the time. So I cover 100% of the time if that's true, and that's true 50% of the time So this thing happens 100% of the time, it's 0.5. And the other thing covers 50% of the time. And that happens 50% of the time. So this is 50% times 1/2, which is equal to 75%, which is where that came from. So there's a little bit of arbitrariness to this. This isn't a real problem that scientists are dwelling over. This is a classical sort of problem to illustrate points about what is a confidence set, what is a confidence interval in general. You could extend the same conversation to intervals if you wanted to. I think we would agree this is a terrible answer. This is an atrocious answer. I'm not just picking on frequentist. Not all frequentist answers are like this. We've seen answers where it's like it's doing the right thing. But the confidence thing is, when it first came out, it was not accepted. So people are like, what is this pivoting thing? And what does it mean to cover? What does that actually mean for your data set? And then eventually, enough of those people got an opinion, became professors, and started forcing you guys into this confidence idea and saying, it covers some amount of time. What's the probability that my parameter is in there? And they'll say to you, it's a 1 or a 0. And that never sits well with anybody. It's either in there or it's not, but all I can talk about is this process. And so for this particular data set right here, for a particular x1 and x2, I either covered or I didn't. This describes a process. So I think it's kind of amusing that, I haven't heard this for a long time, but I used to hear it a lot, that, Bayesians need to assume something a priori. Yeah, and we can explain what it means, we can tell you what the properties of the posterior are, but yeah, we accept things a priori. I think everybody does. So that's not really compelling by itself. This is an a priori statement about the coverage rate of a process of collecting data sets over and over and over again. It is not a statement about a particular analysis. So sometimes it might be, but in this case, I don't think we should be reporting 75%. So what that means, if you are just blindly following kind of the frequentist coverage sort of thing, it means that if I got an x1 and an x2, and I was interpreting this strictly as a frequentist in terms of a coverage thing, if I got an x1 and an x2 that were different, I would report that back, and I would, at least if I were blindly doing this, I agree there's better ways to do this, I would report back 75%. I'm 75% confident. And that would be an accurate description. Obviously, this example is meant to kind of beat up on the frequentist a little bit. So if I got this answer right here, if I reported that back and they said, how confident are you, whatever this confidence thing is, I'd say 75%. And I don't think those are good answers. So if you did see this, if somebody came into your office, Christian, somebody walks into your office and says, I saw this scenario, and you computed that for them, what would you tell them how certain you are that it covers? Assuming this is true.
I mean, my big objection, I guess, I'm sorry, the thing that was clear in my head was that this is way off, essentially 25% of the time, so I would say the certainty is way low. I don't want to
Anybody else want to quantify? 100. So I would feel pretty good about it. I would want to report back to the person, I'm 100% on this. So that's on the top line. So for this case, if I saw this, I would probably want to report, I'm 50%. Now that is a frequentist answer as well. And I would say that's what we call the conditional frequentist. And so there's something called the conditional frequentist where you're conditioning on cases, and we never study this for a reason. It's because there's no paradigm for actually building the conditional frequentist answer. Maybe a Bayesian can do it sometimes. We're always conditioning on the data. But the conditional frequentist answer is supposed to condition on an ancillary statistic that's a statistics such that the probability distribution that does not involve the parameter at hand, it's on its own non-informative about the parameter. The sufficient statistic that you might focus on is x1 minus x2. And so if this is equal to 0, maybe we'll do the absolute value. If it's equal to 0, for the record, this is an ancillary statistic. So if I take a shift parameter and I subtract it from each other, you've always knocked out the parameter. So if this is a 0, then I might report back this is a 100% covering answer. Or if this is a 2, right here the difference between them, x minus 1 and x plus 1, the difference between them is 2. So you can do the math in your head. I'll double check. Yes, it's 2. Then I might report back 50% of the time. And the paper I'll show you does have a passage on the conditional frequentist. And they'll kind of talk about nobody's come up with a coherent framework for doing that, because you need to come up with the right ancillary statistic to think about to condition properly. And nobody knows how to do that. So I don't know how to do it. And Jim Berger, the author of the paper that I'll send to you, he also does not know how to do it. So, and that's the argument he makes. So there are other ways of constructing a confidence set that might be more interpretable, but on its own, confidence doesn't tell you that. So you don't know, does it actually cover, do I feel good about this 75% answer? I think the answer is terrible. So this is an a priori statement about whether or not I'll cover if I keep repeating this process over and over and over again. What does that mean about your belief about the parameter? I certainly would not be reporting back 75% if I solved that versus that. I would feel much better about reporting back 100% and 50%. All the same, that is a 75% confidence set. So I don't think it's too outlandish to say that's a terrible answer. So, but it highlights at least a pitfall of just being a frequentist. Let's look at what a Bayesian would do. So, Bayesian is very interested mostly with the likelihood function. Always looking at the likelihood function. And I would say for Bayesian analysis, the likelihood function should be the driving force of your inference. And the prior, while it might bias things, it had better give you variability back, a decrease in variability. So overall, the prior can help you to regularize certain cases. Let's just start with the likelihood function. So the likelihood. I can never remember what a likelihood is unless I'm staring at the actual process. So I want to look at the process again. I'll write this down again. Remember, we're just going to see one of two values. This is theta plus 1, theta minus 1. This happens with prop P, which is 1/2 in this case, and that happens with probability 1/2. So same sort of thing. So how do I construct the likelihood function? Both of these realizations that we'll see, x1 and x2, are IID. So I'll say that. Things IID in this problem. So how do I build the likelihood function? How do we always do it? It's no different. This is my favorite question in all of statistics. What's the likelihood? That's my favorite part, is modeling things and building likelihood functions. I usually look at how it constructs data, and I think about it compared to the data that I'm observing. So I think about that frequentist thing, and once I feel pretty good about it, I construct likelihoods from that exact same process. So if you tell me the process that creates the data and I can write it down analytically, I can write down the likelihood function. So what is the likelihood in this case? Here, I'll do the easy part. This is what we're trying to write down. X1, X2. Okay, let me ask a different question. What's the sampling distribution? Can we write that more algebraically? I have it written down as that process sort of thing with the open braces. You just have to rewrite that as a mathematical function. So what's the sampling distribution? Let's just say for x1, for the first data point. I'll make it an I, so it's for any particular data point. Here, I'll do that. I'll do it. Probability of xi given theta. What's that?
Is it just two indicator functions, basically?
Maybe. So right now I'm just talking about the one point. So his two indicator functions comes from the other point. So let's talk about the first one. You're on the right track. You should feel good about that.
Is it Bernoulli?
It's like a Bernoulli thing. Yeah. So what do I write down here?
1/2.
1/2. Sweet. Is that good?
You have to raise it, right, to the power?
I have to raise it to a power. So it's going to be, oh, you want me to do 1/2 times x, an indicator function of xi, or 1/2. It's fine. Get rid of this. So maybe 1/2 times xi is equal to, let me give myself a little bit more room. Xi is equal to theta plus 1 times 1/2 delta xi is equal to theta minus 1. So just to be really clear about this, delta of xi is equal to theta plus 1 is equal to 1 if xi is equal to theta plus 1. So it's just a re-encoding of that variable you saw. So you're just making this indicator function. Delta xi is equal to theta minus 1. Oh, and I should say 0 otherwise. Same thing. This is going to be a 1 or a 0. And this is if xi is equal to theta minus 1. That's if it's different. Xi is not equal to theta minus 1. It's a switch. You guys are all familiar with the delta function notation. If the argument inside of it is true, then it's a 1. And sometimes people will put the argument down at the subscript and have an argument in the front if those things are equal. Notation might change a little bit, but it's just a 1 or a 0. So it's either this or it's that. Now, if I change the probabilities a little bit, this might be a different number. The beauty of this is always 1/2. If that's a 0, this is a 1. That will be a 1. Right here, it's the other situation, so that'll be a 1/2. So on and so forth. What do you think of that? Like it? Does anything stand out at you that if I'm about to take this and turn that into the likelihood function, does anything bizarre happen? So I might do something like this. So this is going to be, I goes from 1 to 2, fxi, given theta. I put probability, that's cool. Probability. So in any case, that's always a half, no matter what. So that would be, I goes from 1 to 2, 1/2, that's 1/4. Like that. Is that the likelihood function? What's the dead giveaway that it's not the likelihood function? Yeah, the parameter's not in there. This is a flat surface. No matter which xi's I saw, it doesn't change anything. So that means that the likelihood is totally uninformative about theta. And that's troubling. So, so this probably isn't the likelihood function. So this isn't quite right, but we're close. It turns out the part that everybody focuses on first is the wrong part. You know, so everybody will jump over to that 1/2 and write this thing down. So the parameter's not in here, so this whole thing is wrong. Param is not in there. So it's incorrect. Heads up. This is the #1 error you can make in this class. If I see this on a midterm, I spend my whole day in a tizzy. So I lose sleep over it. How could you write down a likelihood without the parameter in there? So that was the whole point, that somehow likelihoods have information and their shapes have information about where the parameter is. I'll lose sleep. Doesn't work out well for you either. So it's bad news. The second biggest mistake is to divide by a matrix or something like that. So the typical thing. But in this class, writing down a likelihood function without a parameter in there is not good. How do we get the parameter in there? Obviously, we didn't do this right. So we have a constraint in here. So xi is either theta plus 1 or xi is theta minus 1. And we haven't built in that constraint. So there's a relationship between xi's and theta, and it is in the constrained values that xi can take on in the first place. We need to create that. So what is a likelihood to me? It expresses the relationship between the parameters and the data. And you can use that in all kinds of different ways. I like to express that relationship. Likelihoods also were not well adhered to early. So I'll bring you some passages later on of statisticians arguing about the utility of likelihoods. What is this thing? So Fisher came up with it. Which is almost ironic. So if you study that history of statistics sort of stuff, it's very ironic that he's the one that presented the likelihood function and said this is the likelihood function. So people have been playing around with likelihood functions for a very long time before Fisher, but they weren't naming it. So Fisher went in and understood lots of properties of statistics and named a lot of devices that we use today. So I think Fisher ended up becoming, at least for a while in his career, opposed to maybe strict likelihood-based methods. So he started arguing against them, even though he comes up with it. I need this relationship in there. How do I force it in there? It's always the same way. So this is basically determining the boundary of your space. Which values can xi take on, or given xi's, which values can theta take on? And so we always do this the same way. So when we're encoding the boundary of the space that doesn't show up in the bulk of the function, we have to shove it in there, we always do it the same way. So another indicator function. So let's just do it. So probability of xi is equal to beta plus 1 is equal to 1/2 times delta function xi is equal to theta plus 1. So what are the other things? So in general, or it could have been, I should just write down in general, xi given theta, it's either that or xi, I'll write it like this, or xi is equal to theta minus 1. I think I like that notation right here. You could have encoded the 1/2 a little bit different and plugged in all of this stuff if you wanted to include the specifics of the indicator functions here. But keep in mind, this 1/2 is that thing right here. And I didn't need an indicator function for that. So it's 1/2 no matter what values the xi turns on, just because the probabilities were both 1/2. So we could mix up the problem a little bit better, but it's made to be simple so that we can do the algebra pretty easily. So it's one of those two things, and so now we've encoded that. So if you want to, you can put a union in there and write it down like that. So it's one of those two things, and now we've expressed the boundary, at least arithmetically. So our likelihood function looks like this. Proportional. I'll write this thing down. I goes from 1 to 2, and it's going to look like this. 1/2 times delta function xi is equal to theta plus 1, or xi is equal to theta minus 1. And that's the likelihood function. And I can power this thing through. But I could also just get rid of this, because that's just a multiplicative constant. So the part everybody does, if you go back through my years of videos on this, this is where everybody writes down the half thing. And it's the part that doesn't have any information about the parameter. So it seems to be a natural tendency. The likelihood function is the product of those two indicator functions. Is that what you said? Maybe. Take credit for it. Yeah. Why not? So this looks like this. x1 is equal to theta plus 1, or x1 is equal to theta minus 1, times this delta function. x2 is equal to theta plus 1, and or x2 is equal to theta minus 1. I'm going to do that pivot thing, but I'm doing it totally for different reasons. I just want to reorganize this. I like thinking about theta. I hate when theta pops up in all these different places. So I'm wondering if I could express this just a little bit differently, and I could do the same thing. So this is equivalent to theta is equal to x1 minus 1. Those are exactly the same statements. And this is equivalent to x1 plus 1 is equal to theta. So theta is either equal to one of those two things. So same statement, and I can do the same thing for this. Let's get rid of this. So our likelihood function for this problem reminding us that we're only looking at 2 data points. What would I really say to somebody? Probably go get some more data until you get a mismatch. So do it until then, and I'll tell you exactly what theta is. So it looks like this. Proportional to delta theta. I'm going to write it a little bit differently. Theta is an element of one of two things. x1 minus 1, or x1 plus 1. So this delta function, there's still one more I'll write down in a second, is exactly that. These are the same statements. So if you don't know this notation, this means element of. If you don't like writing it that way, you want to write it like that, you're good. So it means it's one of those two things in those sets. And then I have another piece. That's going to be theta is an element of x2 minus 1, x2 plus 1. That's the second indicator function. That's the likelihood function. And for me, I would look a lot at this thing. I'm not prepared to do a Bayesian analysis. I like thinking about what the likelihood function looks like. And if it were up to me to go back 100 years and rebrand all of statistics, I'd get people to write down likelihood functions. So if we did that, I think we could at least be on similar pages. So what we do with the likelihood function might differ a little bit. I like people thinking about that shape because I think it has information. There's something called the likelihood principle, and I'm not prepared to open that can of worms right now. So, because I think it's a little overstated. But some people believe that your connection between the data and the parameters must only come through the likelihood function, and everything else is wrong. I don't believe that. So I think if you do form those connections through the likelihood, very little can go wrong for you, but there's other ways you can do things and think about things. So I like doing this because it gives me at least plausible answers. It puts them in the right ranges. It adheres to the bounds, and it conditions properly. So it contains all the sufficient statistics and all the ancillary statistics. So any statistics I needed to condition on, it does that, and it conditions on the full data set. And so it adheres to the conditionality principle. So your answer should be conditional on what you have observed versus this whole process interpretation of things. I like all of those things. So we just need to visualize that, what it looks like. So let's just pick a couple numbers because I have a hard time seeing functions. So let me just say, let's change it, that theta is equal to a 3. This is the truth. If I were building a simulation study, I would get to know this, and I could compare my answers to the truth and check if I'm covering or something like that. So let's say this is the truth. So there's two different cases. So case 1 is x1 is different from x2. In case 2 is they're the same. Okay. So let's give us some numbers just so we can think about this function. We know what those two numbers are in this case. So we're going to see a 2 and a 4. It could have been the other way around. We don't know. So I'm just assuming that x1 was the theta minus 1 thing. So true theta is 3. They're not matching each other. It's all independent stuff, so I can shuffle them. The order doesn't matter. And I observe this right here. So let's just draw this likelihood function. What does it look like? I have to go back to the formula and plug these numbers in right here. So x1 was a 2 right here. I'm just giving us some numbers so we can think about it. So I've said x1 was a 2. And so that thing is either, that's a 1, or this is a 3. x2, I'm saying is a 4. So this right here would be a 3, and that thing would be a 5. So if I product these two things together, those are the only values that these can change on. You could switch the order of those. I pre-assumed I know which one it is, just so I could write something on the board. But if this was a 1, right here, theta was a 1, this indicator function would be a 1. This one doesn't have a 1 in there, and this indicator function would be a 0. So the value of this likelihood function at 1 would be a 0. At 5, the same thing happens. This indicator function would be a 1. That one would be a 0. And something magical happens. So when this is a 3, that's a 1. That's a 1. This thing is a 1. If it's any other value of theta, both of them are zeros. And so the likelihood function looks like that. All I'll just write this down right here. Let's say that I ended up seeing that this thing was a 2. So that thing is a 2 as well. So this, if we do the same arguments, this is going to peak at 1, or it's going to peak at 3, the likelihood function. So in this case, I had x1 is equal to x2. I arbitrarily said that it was a 2. It could have been a 2 or a 4, one or the other, with probability 0.5. So I arbitrarily picked one, said that that thing is a 2, and so same thing happens. That set of indicator functions, because I would have a 1 and 2, sorry, this would be a 1 and a 3. They'd be exactly the same thing, so they would peak twice in here. And it'd be a 0 everywhere else. So this sort of thing you could think of, it doesn't matter what the height is. But I think we're starting to see some information. And it wasn't because we were a Bayesian. It was because we were actually just following the conditionality principle and using likelihood functions. So likelihoods themselves are great. I love them. So let's come back next time, finish up the analysis, but what you're going to do is you're going to come up with a prior. You might be thinking of a flat prior, and then you would calibrate this to a probability space. These would be equally heighted, these 2 points. And so you'd probably calibrate, if you use the flat prior, this would be probability 1/2, that would be probability 1/2. And no matter what prior you used over here, so long as you put mass over the truth, it would be probability 1. You would know with certainty what the true parameter is. Let's come back, philosophize just a little bit more, and then after that, I'm going to give you a prelude to MCMC. So we're going to switch gears completely, get into computation, and then we'll combine the two things, and I'll show you how Bayesians use MCMC. No class on Friday. We'll meet next time on Monday. There'll be a review session on Tuesday. Great week, you guys.